Hi, my name is Rose. I'm a PhD candidate at Stanford's Computer Science Department, and today I'm going to talk to you about my work on bridging the novice-expert gap via models of decision-making with my collaborators Ashley, Carly, Susanna, and Dora. So first, let me situate my work in our math education landscape. We know that a student's math education experience plays an incredibly important role in their future professional success and academic success. For example, prior research indicates that high school students who complete more challenging math courses are less likely to be unemployed. Additionally, those students are more likely to graduate from college. However, our math education system faces huge challenges. Following the disruptions of the pandemic, national test scores plummeted with the single largest drop in math in 50 years. Additionally, while the largest drop happened during the pandemic, topics like data and statistics started declines pre-pandemic as early as 2015. Tutoring has been shown to be one of the primary and most effective ways to combat pandemic-related learning losses. However, to accommodate for growing demand for tutoring, many tutoring providers hire novice tutors to deliver instruction. And while novice tutors may exercise content knowledge, they often lack the specialized training of professional educators in interacting with students. Mistakes are a prime learning opportunity to address misconceptions, but novice tutors struggle to effectively address them because it involves pedagogical expertise and engaging with the student's thinking. This is particularly important for young students. Let's consider this real-world tutoring example where the tutor and the student are working on this math problem shown here. The tutor gives the student this problem. Mike has 4 cookies and he eats 3 cookies, so he has how many cookies left? And the student makes this mistake of saying that Mike has 10 cookies left. In our work, we see that novice tutors tend to give away the answer or explanation without engaging the student in critical thinking. In the era of LLMs and ChatGPT, automated tutoring has resurfaced as a way to scale high-quality tutoring. However, are today's chatbots good enough to become math tutors for young students? A lot of my work, including this study, has shown that out-of-the-box LLMs do not carry the pedagogical expertise needed to perform remediation, as one example. When prompted to generate a useful response to an elementary student's mistake, LLMs also give away the answer and explanation. And these aren't just cherry-picked examples, nor a small matter. A pilot study from Khan Academy deployed Khanmigo, a ChatGPT-powered bot, in a real school district that had similar findings. LLMs gave away answers to students, and the school district had real concerns about Khanmigo not engaging the students in critical thinking skills. Yet we know that good pedagogy to scale is really challenging and expensive. Experienced teachers are limited while they do carry the pedagogical expertise to meaningfully engage with students. And so the insight of this work, inspiring our method, is can we first understand how experts think about remediation in order to scale high quality tutoring? My work builds on prior literature in cognitive task analysis to answer this question. So cognitive task analysis, or CTA, deals with uncovering the latent decision-making processes of experts behind their observable actions across a range of domains such as education, medicine, and law. One example that I really like is an application of CTA in a slightly more niche domain, namely high-altitude mountaineering. So this work that I'm showing here looks at the cognitive processes of high-altitude climbers in deciding whether or not to continue climbing. The observable here is the decision of whether or not to continue or turn back. And CTA surfaces their decision-making steps, such as whether to infer weather patterns to even factoring predictions about their chances of frostbite and summiting. A core application of these CTA models is to close knowledge gaps between experts and novices through real-time decision aids. It makes these hidden decision-making processes explicit, which can be extremely useful for training novices about how to solve for tasks. And while there's been previous works in CTA that model decision-making processes for discrete actions, like in this case, whether to continue climbing, less work has been done in synthesizing models of expert natural language responses or contributing a data set with expert decisions. And that's exactly what our work bridge contributes. So returning back to our challenge, we want to be able to model the latent decision processes of experts behind their responses. And to do this, we use CTA methods. So first, I want to chat a little bit about the kind of data that we're working with in our setting. So we collaborate with a tutoring platform in a southern school district serving over 30,000 students. And the tutoring sessions are typically happening with 3rd grade to 8th grade students with real human tutors. A majority of these schools are classified as Title I schools, and 3/4 of these students identify as Hispanic Latinx. In our work, We extensively work with 4 experienced teachers, each with about a decade's worth of teaching experience. And over several months, I work with them to understand their remediation decision process. And so for developing that type of framework, we pay them at $50 an hour and $40 an hour for annotation after we've established the framework. All of this is to say that we took several measures to ensure that the data collection was high quality, that this data set was valuable and real world, and in particular that the experts' decision annotations and responses are faithful to real teaching practices. And so we believe that this data set is a really valuable resource for providing real equitable learning experiences in the future. And so onto the CTA process. So for CTA, what had happened was that I provided these experts the conversation examples containing student mistakes. And I asked them to directly revise the tutor's original remediation response to be more caring and useful. And so the experts and we met on a weekly to bi-weekly basis where we went through each of the revisions and discussed their approaches to each of the mistakes. And I used 3 core questions to facilitate this discussion. One was, what did the experts notice? How do they want to react to the student's mistake? And why do they want to react in that way? Several themes emerged after a few meetings. So based off of their own teaching experiences, these teachers inferred the student's level of understanding as context for their remediation response. This resulted in the first step of the decision-making model to infer the student's error to answer that first question there. What had also come up was that experienced teachers use several different strategies or techniques to engage with the student's error, such as asking questions or simplifying the problem to meet the student's level of understanding. The diverse strategies led to the second step, which is determining the strategy. And finally, the experts also use strategies for different ends depending on the error. So for example, they might use the same strategy of asking a question to either hint at the mistake or diagnose the student. This insight resulted in identifying the intention behind the strategy. And there were several validation steps that I performed to ensure that this type of decision-making model could generalize to other tutoring sessions and other teachers, which you can read more about in our paper. Our bridge work contributes a high-quality real-world data set with tutoring conversations across 120 math topics and with doubly annotated expert decisions and responses. You can find our data set and more details on our work at this GitHub link or that QR code. And so on to the results. Does Bridge actually improve the model's ability to remediate? In our work, one of the experiments that we perform is a blind rating evaluation by a set of teachers. And we asked these teachers to compare responses from the original novice tutor with different responses, either coming from the human expert or from different models like GPT-4 or GPT 3.5, as well as these models augmented with our Bridge framework. And so we asked these teachers along various axes motivated from the math education literature and conversation dialogue literature, whether or not they prefer a certain response, think the response is more useful, caring, not robotic, and then aggregate their overall score. And what we show in our work is that just out of the box, these LLMs don't perform as well as human experts, which you can see particular in their aggregate score, that the human experts perform much better than they are. However, when augmenting these language models with these explicit experienced teachers' decision-making steps, such as what they think the error is and the type of strategy they want to use, we are seeing a significant improvement in the model's ability to remediate. And you can find more results in the paper, including other ablations and other models that we either fine-tuned or zero-shot prompted. Another type of analysis that we perform in our work shows that the models are able to improve in terms of their language use with engaging with the student's process. So before we had seen that out of the box, most of these LLMs just gave away the answer or just provided very outcome-oriented responses. Whereas now with augmenting these models with our Bridge framework, we're seeing that the model is able to engage with the student's problem-solving process as indicated here in the blue marked words. One really striking observation in our work is just how incredibly diverse human decision-making is compared to the decision-making made by LLMs. And so what I'm showing you here is is different decision-making paths in our data set, where a teacher might identify a certain type of error shown in red on the left-hand side column and will want to remediate with a corresponding strategy shown in green to then towards what type of intention shown in blue on the right-handmost column. However, if you prompt LLMs to make the similar types of decisions on these tutoring scenarios, what we see is that they're incredibly homogeneous in terms of their decision paths. So you can see here as an example, GPT 3.5 primarily uses the strategy of just providing a correction towards the end of just directly correcting the student's mistake, as we had seen in some previous examples before. And so you can find more types of analyses like these in our work. So now to summarize our work and to hint at next steps for Bridge, in our work Bridge, we showed that teaching is incredibly hard. A lot of the hard work is actually stuck in this hidden decision-making phase that are being made before we actually observe any response written from these experienced teachers. And so the insight of our work is that we need to be able to explicitly model the internal decisions of real experts, such as with our method Bridge. Now, the natural follow-up to our work, as we've shown that LLMs can really benefit from Bridge, is whether or not real human novice tutors can also benefit from Bridge. And so currently I'm conducting an ongoing randomized control trial where we build this tool called Tutor Copilot inspired from Bridge to see whether or not novice tutors also benefit from these types of decision aids when performing real-time tutoring sessions. So stay tuned if you want to learn more for those results, but thank you for listening.